Okay, so we began counting and we did a couple of methods for counting that generally doesn't sound like very fancy thing, so but on its own, but then when you combine them with other techniques, then it can solve really deep questions. So you're going to learn a few more counting methods and some other concepts related to counting. So hopefully you'll finish it today. So the first thing we saw was the sum rule, and where did you get this? Okay, so the sum rule, where we want to find out essentially the cardinality of two non-intersecting sets, the union of the two non-intersecting sets, right? So yeah, can you please stop talking? So we said that if there is a procedure can be done in n1 ways and or in two different ways, then the total number of ways you can do the procedure is n1 plus n2. Then we talked about product rule, which is if a procedure can be broken down into two tasks or more than two tasks, successive tasks, and if task 1 can be done in n1 ways, and for each way of doing task 1, task 2 can be done in n2 different ways, then the total number of ways you can do the overall procedure is n1 times n2. And the complement rule is not really a method. This is a simple trick that if sometimes you find it difficult to compute the cardinality of a set, you instead compute the cardinality of the complement, and complement is defined with respect to some universal set. So there is in the background there is a universal set, so that helps you find out the cardinality of the given set, right? Now we do inclusion-exclusion, which is exactly the sum rule. This is actually the generalized sum rule. The proper sum rule is this thing, okay, for two sets or multiple sets. So we remember this question, we did this. Suppose I have 32 students in one section and 35 students in another section, okay. Suppose I give the grade A to one student. How many choices do I have? How many choices do I have to give A to some students? So I can give out A. What are the possibilities? Who will get A? How many different possibilities are there? You? Oh, I thought you said I will get A. Okay, so you want 32 plus 35, right? Suppose I have 32 students in the discrete math course and 35 students in a programming course, and so I give out the A grade to one student. So how many choices do I have? 32 plus 35, right? Do you see any difference between these two things? What's the difference? हो सकता है somebody is in this. So then the number of choices is not actually 32 plus 35, right? Because those students who are in both two different courses, the first one we studied earlier, and that's correct, 32 plus 35, because there are 32 choices that these names will appear, because there is an assumption that a student cannot be in both sections of the same course, right? But for different courses, there could be student taking both courses. So now that's not really a different option, right? So I don't have 32 plus 35 options. And this type of thing is exactly the sum rule, but we have to qualify it, right? Doesn't work for the thing we studied so far only works for non-intersecting sets. So this is basically the sum rule, the detailed sum rule, or what's called the Inclusion-Exclusion Principle, is the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A intersection B, right? In the previous sum rule picture, we saw that there was no intersection between these two, so the formula is still valid, except for this cardinality is 0, right? So cardinality of A union B is the cardinality of A plus the cardinality of B, but it doesn't have to be the non-overlapping sets. They could overlap, and this way we can count the cardinality. Does everybody is convinced that how is this formula come? Like how can you prove this thing? Okay, so the way you would prove something like this is that, so suppose there are certain elements A1, A2, A3, A4 in exclusively in A, and B1, B2, B3 exclusively in B, and C1, C2, C3 so on in the intersection of these. These are elements that are in both, so the red elements of them. Okay. So when I add the cardinality of A, I'm adding those A's, A1, A2, A3 and C1, C2, C3, right? There are 10 A's sets and 5 C's, so this will be 15. And then when I add B, so the cardinality of B is counting those B1, B2, B3 elements, and it's also counting the C1, C2, C3 again, right? So those elements in A intersection B are counted twice. If I'm just counting them and marking them, there will be 2 marks on these elements, once from A side and once from B side. So then I just subtract it out once. Okay? So 10 A's, 5 C's, and then 5 C's again, and let's say 17 B's. Those B1, B2, B3. So those 5 C's that were added twice, I subtracted once. It will give me the exact the exact count of elements, right? Without over counting or double counting those intersection elements. The intersection is double counted, and I remove one thing. The generalized thing, okay, so do this thing. So what is the cardinality of A here? What's the cardinality of A? What's the cardinality of B? 6. What is the intersection of A and B? 7 and 9, right? So cardinality of A intersection B is, no, cardinality of A intersection B is 2. Yes? 7 and 9. So if I take the union, it will be 2, 4, 7, 9, 1, 3, 8, 5. Okay? So there will be 4 plus 6 minus 2. There are total 8 distinct elements. Okay? So A intersection B will be 4 plus 6 minus 2. Does this make sense? If you were just adding A plus B, this 7 will be counted twice and the 9 will be counted twice. Once in the A side, from the A side, and once from B side. So the generalized, slightly generalized inclusion-exclusion principle is as follows, right? And so the cardinality of A union B union C is the cardinality of A plus the cardinality of B plus the cardinality of C. You add all the cardinalities, a lot of overcounting, then you subtract out the overcounting. You do subtract A intersection B, those elements are counted twice. You subtract B intersection C, those elements are counted once from B side and once from C side, and you subtract out A intersection C, right? So those are also counted twice from this. What happens is that those elements that are in A intersection B intersection C, in all 3 of them, this red area, this will be counted once. All these elements, all these red elements will be counted once, twice and thrice, right? So they are counted 3 times. Okay, they contribute to these 3 cardinalities, so they will be, each element there will be counted 3 times. But then when I subtract them, this A intersection B, this region, this will also include these red region, right? So A intersection B, then those elements in the 3-wise intersection are subtracted once, then subtracted again, and then subtracted again. So they are added 3 times and they are subtracted 3 times, right? They don't contribute at all. That's why we add it once more. Does this make sense? Okay. So this is the general principle, and you can do this example, simple, same one, except for B is one step smaller, now. How many distinct elements are there total? What's the union of A union B union C? So 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 numbers in A union B union C. Okay, let's add the cardinality of A plus cardinality of B, cardinality of C. What do you get? 4 plus 5, that's 9. 9 plus 5, 14. So it's a big overcount, right? Look at this element 2, that is counted exactly once. when I add cardinality of A plus cardinality of B, cardinality of C, this element 2 is counted only once, right? This element 4 is counted twice, right? Once from A side and once from C side. Okay, when I added cardinality of C, the element 4 was counted. So, what element is common in all three? Okay, so I will add the 4 plus 5 plus 5, that is whatever, 14, and then I subtract the cardinality of A intersection B. Okay, work it out. We saw the union should work up to 9, but this element 9 is going to be counted 3 times in A, B and C. Then it will be subtracted 3 times when I subtract A intersection B and A intersection C and B intersection C. So then we have to add it once more. Okay, did you write this? Should write some working. Okay, can't just write a number, right? So what is A intersection B or something like this? Today we have some really good in-class problems, so take that in-class problem very seriously today. Okay, let's move further. Any question, any issues, anything that you want to discuss? Is this clear? Why do we add and subtract thing? Because we're going to build upon it in the next formula, general inclusion exclusion. Why do we add, why do we subtract or something? Everything is clear? Yeah. So the good way to do it is just define, this type of statements are proven typically by defining types of elements, right? You can color code them or something. So let's say these elements are called type 1 or A's, these are B's, C's, D, E, F, G. These are types of elements. And then see, when you add this formula, then see how many times the A's are counted, the B's are counted, the C's, the D's, the E's, E, F, G's have as many things you see there, right? Or x1, x2, x3, type 1, type 2, type 3. There are 6 types of elements or 7 types of elements. The red one, the 3 green ones and the 3 blue ones. And you will see this formula just makes sense, right? Everything is just balanced out. Everything is counted exactly once. Okay. So this is what we saw. This is the general exclusion principle. If you have n sets and you want to find the cardinality of their union, then you add. You can't just add their cardinalities because there may be intersection, there may be overcounting, double counting, multiple counting, right? So you add up all the cardinalities, then you subtract all the pairwise intersections cardinalities. Then you add all the 3-wise intersection cardinality. Then you subtract all the 4-wise intersection cardinalities and then add. So alternating sum of the k-wise cardinalities. So the general formula is like this. -1 to the n minus 1. If it's odd number, you add them. If it's an even number, you subtract them, right? The formula, you can prove it in your problem sets. You'll be there. It's a simple proof by induction. You can prove it very easily. Okay. Or work it out the way I just told you for 3 sets, and then you can build up on that for 4 sets and internal n sets. Okay. Okay, so let's do some applications of this. Where do we encounter this? And very simple. It's a simple question. You must have seen this in algebra. How many integers between 1 and 300, when I say 1 and 3, between, that means including 1 and 300, are divisible by 5 or 7? How many integers between 1 and 300 are divisible by 5 or 7, right? So the way to do something, okay, how many integers are divisible by 5? How many integers between 1 and 300 are divisible by 5? Not the number. What? How do you find it? 300? 300 divided by 5. Why? Why do you do 300 divided by 5? Sorry? Every fifth integer is a multiple of 5, right? Starting from 5, 10, 15, right? But, okay, how many, so that's the correct answer, 300 divided by 5. How many integers are divisible by 7?
Ground function of 300 divided by 7.
What function?
Ground function of 300
What is ground function? Floor, okay. Floor. Ground? Who said it? Nobody calls it ground. Round, there is a round thing that is a useless thing, but floor function. So, why then floor of, so every seventh number is divisible by 7. So you do 300 divided by 7, you may get something like 19.4, right? 19.4 in the last sevens, we don't add those things, right? So we do 300 divided by 7 and the floor of it, right? Floor of 300 divided by 7. Does it make sense? So we got so this is a set we define M1, M5 and M7. These are multiples of 5s and multiples of 7. See how they are defined? Those integers that are between 1 and 300 and that are divisible by 7, right? 7 divides those a's. So all those a's we collect them. So M5 is equal to 300 divided by 5. The floor of it is, because it's an integer, so floor doesn't really make a difference. M7 is 300 divided by the floor of 300 divided by 7. And so what is M5 intersection M7? How do we describe them? Those are numbers that are divisible by both 5 and 7. So those are multiples of 35, right? It's the same thing. How many numbers are divisible by 35? 300 divided by 35 floor, right? So now how many are divisible by 5 or 7? This is actually the union of M5 and M7, right? M5 union M7 is going to, is the OR, union is like OR. So this will be M5 union M7 will be cardinality of M5 plus the cardinality of M7 minus the cardinality of M5 intersection M7. So we have all the ingredients, we can just do the arithmetic to get the number. Okay? Okay, so in ICP, how many integers between 1 and 300 are divisible by 3, 5 or 7? How many sets would we need to define to apply inclusion-exclusion?
7.
Which sets? 7 sets?
3 sets.
Which 3 sets?
1 for 3, 1 for 5, 1 for 7.
What?
1 set for 3, another for 5.
Yes, so what should be the name? We just did M3 were those, M5 for those that were multiple of 5. So this will be M3, those elements that are multiples of 3, and M5 multiples of 5, and M7 multiples of 7. And we want to find M5 union M3 union M7. Yes? We want to find a cardinality of M5 union M3 union M7, and we know the inclusion-exclusion formula. So this is how we define M3, M5, M7. What is M3? What is the cardinality of M3? How many elements are divisible by 3? Floor of 300 divided over 3, right? The floor of 300 divided by 3. And M5, floor of 300 divided by 5. M7, floor of 300 divided by 7. We can find similarly the cardinality of the elements, multiples of 21, 3 and 7, 3 and 5, 5 and 7. We saw that in the previous slide too. Okay? And we can find the cardinality of M3 and intersection M5 intersection. What are those elements? What are the elements in this set? Not the number. What are the elements here? Not the number. What are those elements?
The intersection of above 3 sets, right?
Yeah, the intersection. Yeah. Okay, do this one too. Okay, multiple divisible by 7, but not by 5, 3, or 5. Right? Exactly the same thing. Just define M3, M5, M7, 3 sets, and you take the unions. I want to give you one quick application, one very good application that's going to come afterward, but one easy this thing. Okay, so I have these 10 letters available. Okay. So I'm going to make passwords of length 10 from these 10 letters. Okay, passwords of length 10 from these, I just have to reorder these characters to make a password, right? There are restrictions. So because there is no repetition, so I'm just going to reorder, get an order of these things. The restriction is that the password cannot contain the word gulf, G-U-L-F, the word math, and the word boat. So these 4 characters cannot appear in this order consecutively. Does it make sense? It's a very quick thing. Always passwords is, our security people are always do this checking, and the hash functions are defined. You generally cannot have a password where you have your username embedded into it, or your name, or something like this, right? Typically it's easy, it's okay, there are ways to check them, okay? And there are, this has value also, security value, if you don't allow this stuff. So passwords of length 10, no repetition, these 10 characters, and the words boat and gulf and math cannot be there in the password. How would you do that? Please pay attention to me. How would you do that? It's a very interesting question, okay? A very cool trick here. Quickly, forget about the second restriction, forget about these two. Just see how many passwords are there. These 10 characters, passwords of length 10, no repetition, cannot contain the word gulf. How would you find that? We can do it using our methods so far. Product rule, sum rule. Okay, there is two. What is n factorial? Don't throw a word at me. No? There is nothing called n. There is nothing called n. Seriously, understand this thing. When somebody asks you a question, you talk about the question, you discuss the question, you think about the question. Don't think about answers. You begin to think about answer, and some random word comes to your mind and you just throw that. This is always happens, this thing, and that's why you make mistakes. Do not jump to answers. Never jump to answer. Yes, please. Yes. Please.
I think we will take out all the set of passwords with no repetition first.
Okay, that's a good idea.
And then we'll like subtract we subtract we can't have these passwords, right?
No, forget about that. I just asked the word gulf. Cannot contain the word gulf. Cannot contain the word gulf, G-U-L-F. So his idea was to let's find all the passwords. Suppose the second restriction is not there. How many passwords are there with no repetitions?
So in a words with the 4 letters, password must be 10.
Forget about that. No, it's just, if there is only one restriction, this answer this question. How would you answer this question, the first part? The second restriction constraint is not there. How many passwords of length 10 are there with no repetition from these 10 characters? Huh? How would you do that?
We have 10 choices for the first place,
Yeah.
and 9 for the second.
So a password is like a 10 box, 10 lengths. So let's think of it as filling up these boxes. How many choices do I have for the first box? 10. Any of this A, B, F, G can come there, right? For each for each way of filling up the first box, how many choices do I have for the second box? Why 9? Why not 10? Yeah, because no repetition is allowed. So for each way, for a given way of filling up the first box, that character is not an option. The remaining 9 are an option. So that amounts to 10 times 9 times 8 times whatever, right? 10 factorial. Okay. Now let's see. Among those passwords, so this is what you said, count all passwords with no repetition. Among these passwords, find the password which do not contain, the number of passwords that do not contain the word gulf.
Sir, again, we can imagine 10 boxes. So our first case be that the gulf is present in the very first.
Very good thing.
And
Okay.
then we can imagine that we have 6 possible choices for the rest of the box. We can gain from the factorial technique and we can move the word.
Okay. So I'm going to give you exactly the same solution. That was the same kind of solution in my mind. Let me just describe what she said. This guy, stop using phone. So she said, okay, let's see, we can kind of convert it into a sum rule question. Okay, where is the gulf? Count the complement rule. Find those passwords that contain the word gulf, right? That's what we're going to do. Find the passwords that contain the word gulf, and then we'll subtract it from the total passwords. Now, where is gulf? It could be the first place. It could begin at the first place, the first box. It could begin at the second box, the third box, right? So G at the third place, U at the fourth place, L at the fifth place, and F at the sixth place, right? Can it begin at the ninth place? It could only begin at the 10 minus 4 place, right, or something. So seventh place, 7th, 8th, 9th, 10th, yeah, okay. And that's now easy. So that's what I'm going to do, but there is an easy way to do this, okay. Please understand this. Let's count the passwords that contain the word gulf. Okay. The way to do it is treat gulf as a one block, is a one meta character, a super character. Okay, let's call it X, this capital X. That stands for gulf. So I have to count passwords that must have GULF, but now I want that must have gulf as one letter, as a consecutive 4 letter in this order, right? So I make gulf, this word gulf, as one super character, right? So now I have 7 characters, X, and then A, B, H, M, O, T, right? So I have 7 characters. How many passwords are there that can be made of length 7, that can be made of these 7 characters, and this is no repetition. 7 factorial, right? In these 7 factorial passwords, there is the word X there. That X actually, if you zoom into it, it's actually GULF. Does it make sense? So that's how you count it. The X could be in the first place. That corresponds to, in her methodology, when the gulf starts at the first place. This could have X at the right, the last character, and that would be when gulf started at 7th character, 7th GULF. Okay. So there are 7 factorial passwords in which the word gulf is there. Okay. Okay. So I want to find the passwords which what are the remaining? How many are remaining? H? Okay, so what I'm saying is treat this thing as one character. This is one fixed meta character, I will call it X. Okay, if the gulf is here, that would mean I would say, okay, the X is here. Okay, that means the gulf starts in this place. So now I have these 7 characters, 6 this atomic characters, and 7 is this meta super character, and I'm just making the password. Now wherever I see X, X actually is now, so I stick them together, I glued them together, these 4 letters in a fixed order, and I'm going to place it somewhere. Okay, it's easier to do it this way, 7 factorial ways. How many passwords are there with the word math? Exactly the same thing. Math, treat math is a block, and this will be 7 factorial. Now here the question is, how many passwords are there with the word gulf and math? How many passwords with the word gulf and math? So I could treat gulf as one meta character X, and math is another meta character Y, and I have these X and Y, 8 characters are gone, and what is remaining? O and B, right? So I have X, Y, O and B, 4 characters. Find all passwords, all possible passwords. These passwords will have X and Y, so this will have the word math and the word gulf. Okay, there are 4 factorial of them. Okay, gulf and math take 8 characters and 2 remaining characters, which we saw, O and B. कितना factorial? No, there is X and Y and then there is O and B. 10 characters in total. Gulf and Math only takes 8 boxes, right? So the other boxes create other 2 characters. So that's 4 factors. These 10 characters, passwords of length 10, no repetition, cannot contain the word Gulf. How would you find that? We can do it using our methods so far. Product rule, sum rule. Okay, there is 2. What is n factorial? Don't throw a word at me. No? There is nothing called n. There is nothing called n. Seriously, understand this thing. When somebody asks you a question, okay, do this one too, okay? Multiple divisible by 7, but not by 5, 3, or 5, right? Exactly same thing. Just define M3, M5, M7, 3 sets, and you take the unions. I want to give you one quick application, one very good application that's going to come afterward, but one easy, this thing. Okay, so I have these 10 letters available. Okay. So I'm going to make passwords of length 10 from these 10 letters. Okay, passwords of length 10 from these. I just have to reorder these characters to make a password, right? There are restrictions. So because there is no repetition, so I'm just going to reorder, get an order of these things. The restriction is that the password cannot contain the word Gulf, G-U-L-F, the word math, and the word boat. So these 4 characters cannot appear in this order consecutively. Does it make sense? It's a very quick thing. Always passwords is, our security people are always do this checking and the hash functions are defined. You generally cannot have a password where you have your username embedded into it or your name or something like this, right? Typically it's easy, it's okay, there are ways to check them, okay? And there are, this has value also, security value if you don't allow this stuff. So passwords of length 10, no repetition, these 10 characters, and the words boat and Gulf and math cannot be there in the password. How would you do that? Please pay attention to me. How would you do that? It's a very interesting question, okay? A very cool trick here. Quickly, forget about the second restriction. Forget about these 2. Just see how many passwords are there. These 10 characters, passwords of length 10, no repetition, cannot contain the word Gulf. How would you find that? We can do it using our methods so far. Product rule, sum rule. Okay, there is 2. What is n factorial? Don't throw a word at me. No? There is nothing called n. There is nothing called n. Seriously, understand this thing. When somebody asks you a question, you talk about the question, you discuss the question, you think about the question. Don't think about answers. You begin to think about answer, when some random word comes to your mind and you just throw that. This is always happens, this thing, and that's why you make mistakes. Do not jump to answers. Never jump to answer. Yes, please. Yes, please.
I think we will take out all the set of passwords with no repetition first.
Okay, that's good idea.
And then we'll like subtract you can't have
No, forget about that. I just asked the word Gulf. Cannot contain the word Gulf. Cannot contain the word Gulf, G-U-L-F. So his idea was to let's find all the passwords. Suppose the second restriction is not there. How many passwords are there with no repetitions?
So in a words with the 4 letters, password must be of 10.
Forget about that. No, it's just, if there is only one restriction, answer this question. How would you answer this question, the first part? The second restriction constraint is not there. How many passwords of length 10 are there with no repetition from these 10 characters? Huh? How would you do that?
We have 10 choices for the first place.
Yeah.
And 9 for the second.
So a password is like a 10 box, 10 lengths. So let's think of it as filling up these boxes. How many choices do I have for the first box? 10. Any of this A, B, F, G can come there, right? for each value of, for each way of filling up the first box, how many choices do I have for the second box? Why 9? Why not 10? Yeah, because no repetition is allowed. So for each way, for a given way of filling up the first box, that character is not an option. The remaining 9s are an option. So that amounts to 10 times 9 times 8 times whatever, right? 10 factorial. Okay. Now let's see among those passwords. So this is what you said, count all passwords with no repetition. Among these passwords, find the password which do not contain the number of passwords that do not contain the word Gulf.
Sir, again, we can imagine 10 boxes. So our first case be that the Gulf is present in the very first.
Very good thing. Okay.
And then we can imagine that we have 6 possible choices for the rest of the box. We can gain from the factorial technique and we can move the word.
Okay. So I'm going to give you exactly the same solution. That was the same kind of solution in my mind. Let me just describe what she said. This guy, stop using phone. So she said, okay, let's see, we can kind of convert it into a sum rule question. Okay, where is the Gulf? Count the complement rule. Find those passwords that contain the word Gulf, right? That's what we're going to do. Find the passwords that contain the word Gulf, and then we'll subtract it from the total passwords. Now, where is Gulf? It could be the first place. It could begin at the first place, the first box. It could begin at the second box, the third box, right? So G at the third place, U at the fourth place, L at the fifth place, and F at the sixth place, right? Can it begin at the ninth place? It could only begin at the 10 minus 4 place, right, or something. So 7th place, 7th, 8th, 9th, 10th, yeah, okay. And that's now easy. So that's what I'm going to do, but there is an easy way to do this, okay. Please understand this. Let's count the passwords that contain the word Gulf, okay. The way to do it is treat Gulf as a one block, is a one meta character, a super character, okay. Let's call it X, this capital X, that stands for Gulf. So I have to count passwords that must have G, U, L, F, but now I want that must have Gulf as one letter, as a consecutive 4 letter in this order, right? So I make Gulf, this word Gulf, as one super character, right? So now I have 7 characters, X, and then A, B, H, M, O, T, right? So I have 7 characters. How many passwords are there that can be made of length 7, that can be made of these 7 characters, and this is no repetition. Very, very simple statement, very simple statement. If you place more number of pigeons than there are the pigeonholes, then some pigeonhole must have more than 1 pigeons. Does it make sense? If you place 6 pigeons, if you shove them into 5 pigeonholes, some pigeonhole must get more than 1 pigeons, right? Some, maybe more. Many will get 2, 2, and 2, right? There are 6 of them. One box could be empty. Does it make sense, right? If I allocate 7 people to a 6-room hostel, somebody got a shared room, right? There cannot be a one-to-one function. Make sense? There cannot be a one-to-one function. That's what Pigeon-Hole Principle. Very, very simple statement. When I'm going to build a lot about this, and you will see many other examples in the course, and it's very obvious, right? What is not obvious, what's just not clear, that where would it be useful? Where would we actually make use of this, right? So for this, I chose many in-class problems, and I'll just mention some of them. You go and work it out. But I just wanted to tell you how beautiful this thing is and how powerful this thing is, right? How does it help the Pigeon-Hole Principle? Okay. Remember the course learning outcome, right? Now it's going to begin. Suppose you take any set of 5 cards, from one deck, then there must be at least 2 cards of the same suit. Make sense? Can you have 5 cards which have no repetition of the suit? Right? How? Which is the pigeonhole principle here? What are the pigeons? What are the pigeonholes? The 4 suits are what? Those are the pigeons. Those are, yeah. So 5 cards could be the pigeons, and the 4 different suits could be the pigeonholes. And everybody is one from one of these suits, right? So think of that as placing those 5 pigeons into these 4 pigeonholes. Some pigeonhole must get more than 1 pigeons, and that's those 2 cards will be from the same suit. At least those 2 cards. Does it make sense? Okay. If I take 10 cards, what can I say? How many must be of the same suit? 3, 3, 2, 2 is what?
So there could be 3 from one suit, 3 from the other, 2 from one, 2 from the other, or at least 3 of them.
Yeah. So this 3 you cannot avoid, okay? Because if you really want to be stingy, do not want to reuse the suit again, you want to avoid touching too many suits or one suit many a time, you can do this. You just distribute them evenly, 2 plus 2 plus 2 plus 2. You have these 2 left. These 2 have to go to one of these 4 suits, right? And that will have at least 3. It's clear? So the general pigeonhole principle says the following. So in this case, we say the number of cards of the same suit will be 10 over 4, the ceiling of 10 over 4. Okay? Makes sense that 10 over 4 is 3, the ceiling. Okay. If I take any set of 13 people, there must be at least 2 who share the birth month. What are the pigeons? What are the pigeonholes? 13 people, right? Let's say 13 people birth months, they are the pigeons, and the 12 calendar months are the pigeonholes. So if you place them, some pigeonhole must get more than 1 pigeon, right? So okay, so it's by the pigeonhole principle, yes, at least 2 must share a birth month. Yes, please.
So in the previous question, cards one, shouldn't it be 2 because the ones that do not get the extra cards will make it 2 only?
So we said at least some must get at least these many of the same suit.
There will be 2 then.
Who said minimum?
At least.
No, we said okay, let's just, it's going to come in a minute, okay? At least means the maximum has to be bigger than or equal to this. The at least is just a lower bound, doesn't mean it's the min. Okay, so can everybody prove this, right? What the proof would be, by the pigeonhole principle, if I consider these 13 birth months as a pigeon and 12 calendar months as pigeonholes, by the pigeonhole principle, at least 2 pigeons will go to the same pigeonhole. That means at least 2 date of birth months will be actually in these same calendar months. I don't know what's that a number. You can't just throw a number at people. You have to say something, right? So by the pigeonhole principle, that's okay. Let's see. Things are going to get very, very interesting. Okay. Suppose I have 6 exam time slots per day, and we have 1 week reserved for exam, 7 days. Okay, 7 days and 6 slots every day. Okay, the slots are given here. Not important, but just 6 slots. Okay, an exam has to be in, well, it could be shorter, but it consumes the whole slot. Okay, is this clear? Suppose I have 300 exams that I have to schedule within this 1 exam week, right? And naturally, in one room, there at a given time, in a given time slot, at one room, it can be exactly at most 1 exam. Okay, there can be at most 1 exam. You cannot have 2 exams at once in one room. Okay, I have 300 exams to schedule. Question is, how many rooms do I need? So let me just make a question. Look, think of it's an interesting question. Suppose you have only one room. Can you do this thing? Can you do this scheduling? Why not? Yeah, because I have 300 exams and I have one room, 6 slots per day, 7 days, total maximum 42 exams can be scheduled. Okay? At most 42 exams can be scheduled. If I have 2 rooms, at most 84 exams can be scheduled. If I have 3 rooms, at most 42 times 3 exam can be. So this is just the same question but turned around. Okay, I'm just asking from the other side, how many rooms do I need? Wait, so we'll see what is the thing. So what should we do? I want to do this thing. What does the pigeonhole principle tells me? What does the pigeonhole principle tell me? So let's say I have k number of rooms, right? K number of rooms. The pigeonhole principle tells me, oh, but that will be the number of exams. Okay, so I have, how many slots do I have? How many total slots do I have? 42, right? So I want 6, the pigeonhole principle tells me that if I do 300 exams in 42 slots, in some slot there must be at least 300 divided by 42, 300 divided by 42, the ceiling of 300 divided by 42 exams, right? In some slots there must be these many exams. Now that slot, that I cannot avoid, right? That must happen at some slot. So in that slot, at that time, I need 8 rooms, right? If I have less than 8 rooms, I won't be able to do the exams. This constraint will be violated. Is this clear? Okay. So this is the generalized pigeonhole principle that I just told you. We used it actually, and you asked that question, minimum or maximum. The general pigeonhole principle says as follows. If there are n pigeons that are placed into h pigeonholes, right, then some pigeonhole must contain at least the ceiling of n over h pigeons, right? The proof is very simple. Okay, suppose, so the proof by contradiction. Suppose all of them, suppose all pigeonhole get at most n over h, less than or equal to n. Let's say n over h is an integer, so we don't worry about the floor and ceiling. So suppose all the h pigeonhole gets strictly less than h pigeonholes, all of them get strictly less than n over h, strictly less than an integer, n over h minus 1 pigeons, right? What does this mean? How many, what is the total number of pigeons? H and h cancels, actually n minus 1, right? They got actually n, you cannot have n minus 1. If you place n pigeons into h pigeonholes and you claim that all of them are less than or equal to n over h, less than n over h, then I will say, no, okay, it's not n pigeons, at most n minus 1 pigeons. Does this make sense? No? Okay. That's a good thing. This is a simple thing. Let's just do this. The picture will help. Suppose I claim that I placed 10 pigeons into these 4 pigeonholes, and all in the 4 suits I got 10 cards, and so I got 10 cards and no suits have more than 2 cards in this among these 10. How would you prove me wrong? I got 10 cards, no more than 2 clubs, no more than 2 hearts, no more than 2 diamonds, no more than 2 spades. The way you would prove me, well, the maximum you can get is, unless you invented a 5th suit, you can only have 8 cards. 2 into 2 into 2 into 2, right? 2 plus 2 plus 2 plus 2. Does it make sense? So that's what I did. I did this multiplication, right? So if you get 4 suits and each no suit got more than 3, less than or equal to 2, then you can only have 4 into 2, 8 cards. Okay, I have H pigeonholes. Each pigeonhole got less than or equal to n over h minus 1. Okay, so then the total number of cards you that one n cannot be more than n. The total number n has to be less than or equal to n minus 1. That makes sense? Think about it, work it out. Pigeonhole principle is very, very simple, and it's very tricky to use it, right? That's why the tricks and the interesting thing comes actually in the usage of it in the example. What are the pigeons, what are the pigeonholes? Okay, if I take 12 numbers in 0, 1 interval, then at least 2 will be very close to each other. At least 2 will be within 1% of, within 0.1 of each other. Is the statement clear? If I get any 12 numbers in between 0 and 4. So, okay, this is the kind of statement like this. Not everybody can have very different GPAs. Okay, how would you do that? Please go with problem sets and the quizzes in these ICPs, do them, every single one of them in quite detail, okay, not just the sheet thing, in detail to work it out. Yes, please.
Good. Which will be our pigeon. Numbers which are the pigeons.
Okay, that's a good idea. So we have 12 intervals. We have 10 intervals. What is the first interval? 0 to 0.1. And what's the second interval?
0.5 to 0.2.
Why 0.1 in both of them? But if a number is in 0.1, which interval it belong to? Sub-interval. So we'll have to make it a closed, then the other has to be opened. Okay, we make 11 interval. Okay, and just to get rid of that one issue. The 12 numbers are pigeons. These are my 11 pigeonholes, right? So this is left opened interval, or what is called semi-opened interval or semi-closed interval. This is 0 open interval, not containing 0, not inclusive, and 0.1 inclusive, right? Then 0.1 not inclusive here, and these 11 intervals, and I have 12 pigeonholes. If a number is between this 0.3 and 0.4, I will place it in this pigeon, this hole, right? So if a number is between 0.7 and 0.8, I'll place it in this pigeon with this hole, right? So there are 12 numbers, I have 11 pigeonholes, I place them, I will get at least one pigeonhole containing more than 1 numbers, right? At least 2 numbers. And those 2 numbers, the difference between any 2 numbers within this sub-interval is going to be less than 0.1. Okay? Okay, this is a really cool thing, very, very cool thing. Suppose you have a party of n people get together, okay? Some people shake hand, other don't shake hand, right? Every pair, if they do, they shake hand exactly once, right? They don't do it, you know, like this person. Remember that the guy who was, so we had this guy here who he had this habit of saying very, very long salam, and then he would actually shake hand, and every time. I see him like 7 times a day, he'll 7 times, Assalamu alaikum, sir. And then he would shake hand like this with 2 hands, right? And so one day I had this laptop box and something, and he said, Assalamu alaikum, sir. And then he did this. I said, okay, hold on to this. And he learned it, and I said, okay, now shake hand. Then he learned it. Okay, so these people are shaking hand with one hand once only, okay? Not again and again in this party. So you either shake hand with someone or you don't shake hand with someone, okay? One person. Now everybody has a certain number of handshakes that they did, right? So you came to a party, you didn't shake hands, so we'll say you have the number 0. If you shook hand with 5 people, we'll say you have the number 5. Okay? The claim here is at least 2 people have the same number of handshakes. Everybody has the number. They keep a document of how many hands they shook, right? And I'm claiming at least 2 people must have the same number. Does it make sense? Is the question clear? The claim clear? At least 2 people must have the same number of handshakes for any party, any time, no matter how they shake hand, who are friends, who are not friends, and they must have the same number of handshakes. When we do graph theory, we'll do a proper version of this question, much easier to describe, not very easy here. This is clear? What are the pigeonholes? So n people and the number of handshakes. At least 2 people must have the same number of handshakes. Yes? Somebody say something. Pigeonhole principle. Yes? The people are? Okay. So how many pigeons are there? N. Okay. What are the pigeonholes? How many pigeonholes are there then? N minus 1. Why n minus 1? Okay. Okay. So the maximum possible number of handshake is n minus 1. What's the minimum possible number of handshakes? So how many possible handshakes are there? 0, 1, 2, 3 up to n minus 1, that's n. Yeah, so 0 to n minus 1 is n. So n people, n pigeons, n pigeonholes, right? The n people are pigeons. The possible number of handshakes 0 to n minus 1, those are the pigeonholes. N pigeons, n pigeonholes. Pigeonhole principle doesn't guarantee anything. 10 students. Can I make this claim that at least some department must have, at least one department must have at least 6 students? Can I say that? That in no matter how you choose these 10 students, you must have one department representation by 6 at least. Because I can choose 2 from each department, that's one way, and no department is 60. So what is that magic number? So that I can say that no matter which X students you choose, at least one department must have 6 people in that X, among those X.
We can count it like this. Amount to 26. Then the 6th one would amount to 26.
Something like that, but it is a so I'm making this pigeonhole principle statement, right? The claim that pigeonhole principle, but except for that, instead of actual numbers, now it's just put in a variable and solve for that thing. Yes.
So we could divide 100 students into 5 groups of 20.
Sorry.
We could divide the 100 students into 5 groups of 20 students, and then we could use a pigeonhole principle to each one.
Okay, so here's the thing. Suppose n is that magic number. I want to say that the pigeonhole principle, through the pigeonhole principle, I should say that no matter how I choose these n students, from some department, at least one of these 5 departments should have at least 6 students, right? So I want to say that n over 5, the ceiling of n over 5 should be equal to 6, right? Or greater than or equal to 6. Okay, and now solve for n. Solve for n means that n should be equal to, so the ceiling of n over 5 is equal to 6 if n over 5 is bigger than 5, right? So n over 5 is bigger than 5, that means n should be bigger than 25. Okay, each bus has 60 seats. How many total seats are there? So 22 into 60, right? These are total number of seats. These are the passenger seats, okay, not the driver. And so there are 22 into 60 seats, and there are 1,000 people, right? I want to say some bus must carry X number of people. Some bus must carry X number of people. Okay, don't do the calculation. We'll see the calculation later. So I want to make this statement: some bus must carry at least X people. Okay, so let's say something. Can I say that, okay, I sent all these 1,000 people from Islamabad to Lahore or Lahore to Islamabad, and no bus had more than 10 people. If I say, okay, no bus had more than 10 people, everybody went, what would you tell me? I said, in this setting, using these 22 buses, I sent all these 1,000 people, no bus had more than 10 people. How would you prove me wrong, or what would be your argument against to counter my claim? Just 1 second. Is the statement clear?
So even if we use the maximum number 10, so it will be 220.
Yeah, so you say in this way you can only send 220 people. You have 22 buses, you send 20. Okay? No bus hit. So I want to make this statement. Now I know the 1,000, I know the 22, I know the number of seats. I want to say that, okay, what is it that some bus must have these X number of students? How X number of people occupied seats?
Sir, since the number of people are less than the number of total seats that we have, we cannot be certain that some set number of people will always be present in a bus.
No, we can. Let's see. How many seats are there total? There will be 1,000 people, right? How many buses? 22. So let's say 1,000 divided by 22 is 50, right? If all seats, no, I don't know, what is 40, let's say. What is 40 times 22? 880. If all buses have less than 80 students, less than 40 people, all buses have less than 40 seats occupied, can 1,000 people can go? No, right? So if there must be a bus which carry at least 1,000 divided by 22 people. Okay? Okay. Some bus must have at least some seats empty, right? So what is that Y? Some bus must have at least certain number of seats empty. No matter how you send them, you try to increase the empty seats or decrease the empty seats or kind of equalize, uniformly distribute them, whatever you do. This much you have to grant me. Okay, so the pigeons should be the empty seats. How many empty seats will be there? How many empty seats must be there? 22 times 60 minus 1,000, right? 22 times 60, that's the total number of seats, minus 1,000 are filled seats, so the remaining are empty. These empty seats will be in one of these 22 buses, right? In some of these 22 buses. The Pigeonhole principle says these number of empty seats divided by 22 seats must be in one of these buses. Okay? So you don't know there are empty seats? How many total seats are there? How many total seats are there? 16? 60 multiplied by 22, right? That's the total number of seats. How many seats will be filled? 1,000. So the remaining are empty. These empties are in some of these 22 buses, right? They are distributed in these 22 buses. So these are the pigeons, these empty seats pigeons are going to be placed into these 22 pigeonholes. Some pigeonhole must have at least these many. Okay? I have to move a little quickly on this stuff because this I just told you just so that you understand that Pigeonhole principles model a lot of counting question. Okay? How many type questions? Okay. Suppose I take any set of 11 two-digit numbers. I take two-digit number, I add their digits, take the absolute value, add or subtract their different digits, right? And subtract their digits and take the absolute value, right? Some two numbers must have the same absolute difference between digits. Any set of 11 numbers, how many two-digit numbers are there? How many two-digit numbers are there? 90 or something, right? So from 10 to 99, right? So there are these, among these 90 numbers, you take any set of 11 numbers, right? Suppose you choose 37, right? So the absolute difference of digits is 7 minus 3 equal 4, right? Or 3 minus 7 equals, the absolute value is 4, right? Each number, you chose 48, so it will be 8 minus 4, 4, right? You chose 73, so that will be, let's say 72, that will be 7 minus 2, 5, right? Or 2 minus 7, absolute value 5, right? So you get these 11 numbers, you will get those 11 differences, right? The digit differences, absolute value of digit differences. And what I am saying, that at least two of these differences must be the same. Why? What should be the pigeons? Those 11 differences. What are the possible differences? How many different differences are possible? When you do subtract two single digit numbers, it will be between 0 and 9, right? The possible difference is, single digit difference is between 0 and 9, right? So there are 10 possible digits differences and there are 11 numbers. 2 must have the same digit differences. 7, 3, 4, right? Any of the ordering, right? Like all possible ordering of these 3 digits, right? You can make certain numbers from it, right? All possible ordering of them. You get a 3 digits number, right? 934, 943, 439, 493, 349, 394, right? These kind of, you get these numbers from them. Now, you take any such, among any 3 digits number written this way, there will be 2 whose differences is a multiple of, whose difference is a multiple of 5. Multiple of 500, sorry. Is the question clear? Three different digits, write all ordering of those digits. Let's say, how many different numbers can I create? Do the first part of this question. How many different digits can I make? Sorry? I can make, how do I make a number? Choose 3 numbers, 3 different numbers, and write in all different ordering. So how many numbers can I make? Sorry? How many numbers can I make? 100 is not a thing, no. 3 digits, different digits. 9 times 8 times 7. I have to make a 3 digits numbers, different digits, right? So how many choices do I have for the first digit, for the first box? 1 to 9, there are 9 digits. How many choices do I have for the second one? 8, because these are going to be distinct digits, right? And how many choices do I have for the third one? So there are 987 different numbers, right? 987 different numbers that I can make, right? 9 times 8 times 7, sorry. What is it? 500 what? 504 different numbers that I can make. My coffee is run out and now I'm just out of charge. Okay. It's generally these people refill it, but now okay. So these 504 different numbers. I'm talking about 504 different numbers. Okay. If I divide them by 500, how many different remainders will I get? You can pick it. Remember when we studied relations, we said the remainder is between the division algorithm, remainder is between 0 and 499, right? So how many different unique remainders are possible? 500, right? 0 to 499, 500 remainders possible, right? There will be 2 numbers among these 9 times 8 times 7, 504 numbers. There will be 2 numbers whose remainder when divided by 500 is equal, right? Does it make sense? Whose remainder when divided by 500 is equal. That's why their difference will be multiple of 5. No? Multiple of 500. So I don't know if you can picture that division algorithm thing. if a number is, let's say, the remainder is 483, there is another number, different number, whose remainder is also 483. That number must be actually 500 away from this number, right? Yes. So their difference will be multiple of 500. That's what it says. Okay, work it out. Don't worry about the details. This is the last one, and a very important one, very beautiful one actually. If I take any set of n plus 1 numbers from the first n to n numbers, first 2n positive numbers, n is a fixed number. If I take any set of n plus 1 numbers, there will be at least 2 numbers among these n plus 1 selected one which have no factors in common. Remember this thing we proved by contradiction long ago, that if a number x divides in another number y, then it cannot divide y plus 1, because otherwise it will imply that x divides 1, right? No number divides 1. Okay, there will be 2 numbers who, among these any n plus 1 number, there will be 2 numbers who have no factors in common. Let me give you a hint, an easier hint. Among any set of n plus 1 numbers, there will be 2 consecutive numbers. If they are consecutive numbers, then they cannot have a factor in common. Okay, so read the question. How many numbers are we selecting? N plus 1. Where are we selecting from? From 1 to 2n, right? So first 2n numbers. I am going to select n plus 1 numbers. And now I am saying, no matter which n plus 1 you select among these n plus 1, among these 2n numbers, no matter which n, how many times everybody selects different one, in every time you select n plus 1 numbers, there will be at least 2 numbers among these n plus 1 that have no factors in common, that have no common factor. These numbers are called relatively prime. They will be relatively primes. Why will they be relatively prime? We saw this lemma in the proofs time, that if a number x bigger than 2 divides y, then it does not divide y plus 1, right? Because that would mean it divides y and y plus 1, that means it divides 1. No numbers divide 1, right? No numbers bigger than 1 divide 1. So essentially the statement is saying that if you have 1 to 2n, you choose n plus 1 numbers, you must choose 2 consecutive. Yes? Can you choose 10 numbers, can you choose 11 numbers from 1 to 20 such that no 2 are consecutive? Yes, choose it, yeah. 11 numbers from 1 to 20 without choosing consecutive numbers. Huh? You can, the most you can do is 10, right? 11th one must be consecutive with someone. Yes? So if you choose, that's n is, in my case n was 10 and 2n was 20, right? So choose any n plus 1 number among 2n, the first 2n, you must choose 2 consecutive ones. And 2 consecutive numbers do not have a common factor. The pigeon will be the n plus 1 chosen numbers. Pigeonholes will be n, there will be n pigeonholes. The pigeonhole will be these consecutive pairs. You have a quiz tomorrow, right? Next time? It will include all of this stuff, okay? When does the other class have it? They have quiz tomorrow? So we are ahead of them? Why? No, not the quiz thing, in contents.
We have a class before they have. So this week we have it on Monday and Wednesday, and Wednesday they'll have it on Tuesday and Thursday.
Their quiz is on Thursday, Tuesday, tomorrow.
We'll have on Wednesday, and they'll catch up on Thursday.
Sir, last Thursday was a break holiday. So did
Oh, that they cover up. No, that they made up. They had an online class or video lecture or something. That's not okay. So we are out of sync now. We are just going in a parity is broken, right? Why?
Because they had the entire class today, and they will only have half of the
They had entire class today. We had today.
class today, and tomorrow they'll have half the class. It was 1%.
Yeah. So why did we go out? We thought we'll go throughout in sync mode. So,
So we'll be in sync after this week.
huh?
After this week, we'll be in sync.
Okay.
So we have one class. We have classes Monday, Wednesday.
No, I'm saying why did we switch the exam, the things, the quizzes? Generally, the quizzes should have been on their first day of classes, or both first days or both second days, right? So it should be either Monday, Tuesday, or Wednesday, Thursday. But then they were going all the time following us, right? And they were cheating with it. I don't know what is going on with this country. Okay. Okay, please pay attention. Pay attention to me. This, you must have seen it in many places, many times. Now we have all of the machinery for it. We're just going to define some words and connect it to our set theory knowledge and other stuff. And we'll then build upon this a lot of other things. Okay, so how many ways you can arrange these letters A, B, C, D? How many ways you can arrange these letters A, B, C, D? 4 factorial. Yeah, can you please stop this? 4 times 3 times 2 times 1, right? 4 boxes, fill up first one with any 4. How many ways can you arrange, how many 5 digits code can be there, with no repetition? 10 into 9 into 8 into 7 into 6 or into 5 or whatever, right? So 5 boxes, the first one can have 10 options, the second one has 9 options for each one of that, and the third one is 6 option or so on, right? Okay, how many ways can you arrange n letters? N factorial. N boxes, n letters. Arrangement means just rearrange them. You don't repeat, you don't omit any. It's n factorial. How many ways can you arrange r digits code, r character code from n characters with no repetition? R boxes. How many choices do you have for the first one? It's exactly the same question as this. Here the digits tell me that there are 10 characters total and 5 is R here, and digits, those are digits there. Here are just generalized symbols, right? N symbols. How many? 9 N, yes. Yeah, we have R boxes. For the first one we have n choices, for the second one we have n minus 1 choices, for each one of the first two we have n minus 2 choices, and so on, right? So it's n into n minus 2 all the way to n minus r minus 1. Minus 1 choices, the third one is n minus 2 choices, and so on, right? So this is, when I say second one has n minus 2 choices, it's a long sentence, okay? For each way of doing, for each choice of the first box, there are n minus 1 choices for the second box, right? For each choice of the first and the second box, there are n minus 2 choices for the third box, okay? So the number of permutation of n objects is n factorial, right? We define an R permutation out of n objects or from n objects is an ordering or is an arrangement of R out of n objects, right? Two things to do. Choose R objects and choose an ordering of that, right? Choose R objects and choose and then fix and then permute them, then find an ordering of that, right? So this way, this is the 5 digits postal codes from n digits, or the R digits, R character arrangement from n characters. The number of ways to do it is n into n minus 1 into n minus 2 into all the way to n minus r minus 1, right? This follows from the product rule, right? We have n objects total. We want to find arrangement of r objects out of them, right? Fill up r boxes. The first box has n choices. For each way of filling up the first box, there are n minus 1 choices for the second one. For each way of doing the first two, there are n minus 2 choices for the third one, and so on, right? So this is n into n minus 1 into n minus 2, so on. Okay. So we give it a number, this big ugly number. We give it an easy way to call it PNR. PNR, the permutation, the number of r permutation out of n objects, right? Number of r permutations out of n objects, or number of r permutation of n objects, is the number of ways you can permute or order or arrange r out of n objects. Okay, this is equal to n into n minus 1 into n minus 2 into n minus 3 into n minus r minus 1, right? Simple product rule, nothing fancy. There is no deep concept here, okay? Just words. The rest is just product rule is the way to do the method to do this, okay? So this is equal to n factorial divided by n minus r factorial, okay? Just to see, just multiply, continue this product up to 1, and then also divide by the whatever additional thing you do, right? So if you multiply this with n minus r factorial and divide it by n minus r factorial, you're going to get exactly that thing, PNR, that we got from product rule, but this is easier to write and easier to describe, right? Just one division, this way is too many multiplication, okay? Is this clear? The number of ways to permute r out of n objects is PNR. The value is equal to n factorial divided by n minus r factorial, okay? So suppose I have 5 students and I give the prize 500 and 300 to first prize holder and the second idiot. So how many choices do I have? Remember last time we were giving a grade, right? Now you're getting dollars, right? $500 and $300. How many choices do I have? Sorry? 9 choices. Not number, no, just not the number. Not number. Not numbers. How do you do this? Okay, so my choices is what choices of what? Choice of choosing someone for the $500 or picking someone for the $300. Fill up these 2 boxes. The 500 box, remember that Olympic stand, right? So who is going to stand on the $500 thing and who's going to stand on the $300 stand? How many choices do I have for the $500 box? 5. For each way of for each choice of the 500 guy, how many choices do I have for the 300 box? 4, right? So it's 5 times 4, right? Which is exactly how we define the number of ways you can arrange 2 objects out of 5 objects, right? And P52. P is a function, takes 2 parameters. The first one is that n, the second one is r, right? Okay, suppose I have 5 students and I give the grade A to 2 students. How many choices do I have? No, I have to choose 1 student. No, A to 2 students. Now, look at the Olympic stand, right? I'm not saying this is not this stand, 500, 300. Now they are the same, both get A, right? So if I write Ahmad Fatima, it's the same as write Fatima or Ahmad, right? Both will get A, no distinction. Yeah, so that's the value to do. So let's do this. So this is the previous one, which we did. You see the title of the thing is ordered versus unordered, right? So now we're going to do this thing. How many choices do I have for this thing? AB is not the same as, is the same as BA, right? Okay, so the number of 2-letter arrangement, the number of these 2 students for 500 and 300, we saw that was P52, it was 30 of them, right? 20, okay? So if I list all these 20, just think of these 20. Suppose I think that these 20 are the choices that I have to give them A grade, right? The problem is I will be counting this DE and ED actually is the same set of people who both get A. I'm counting them twice if I do the ordered arrangements, right? So, but I know exactly how many times. Suppose ED is what I'm choosing to give them A. How many ways can I arrange this ED among themselves? How many ways? How many ways? If I choose these E and D to give them grade A, but by mistake, how many times would I write them in different ordering? Sorry? How many ways can I arrange E and D, the letters E and D? 2 factorial, yeah, which is 2. 2 factorial is the right answer. I told you, you have to say what I want to hear, okay? Not say what is correct. Well, what is correct is also okay. So it's 2 factorial, right? So I'm going to this over counting. Each ordering is counted 2 factorial times. So I'll just factor it. I will make that a factor, right? So I will just divide them by 2 factorial, and this will give me the answer of the number of actually unordered collection of R objects out of N. Okay. So this gives us this thing. Okay. How many subsets of size 5 are there for the set 0 to 9 10 digits set? How many subsets of size 5 are there of cardinality 5? Keep the calculator away, please. I'm not interested in numbers. Answer the thing. To do this your ICP, you have to do it on paper. How many subsets of size 5 are there? How would you do it? How many 5 permutations are there? How many 5 permutations of these 10 objects are there? P10 5. We gave it a name, right? We know the number of ordered permutation, ordered arrangement of R objects out of these N objects. That is P10 5. In each of that, how many times, let's say 1, 2, 3, 4, 5. How many times is that set 1, 2, 3, 4, 5 counted in this number? 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. 1, 2, 4, 3, 2, right? Or whatever. How many times these 5 digits are counted and how many arrangements? That's 5 factorial, right? That was our first question. How many ways to arrange 5 objects? 5 factorial. So you divide this by 5 factorial. That's actually P55 or 5 factorial, and this will give you that each subset is counted 5 factorial time, which is 120, right? So you divide Pnr by R factorial, you get the number of R subsets of size n, right? From a subset of a set of size n. Okay, so in this case the answer is P10 5 divided by 5 factorial. That should be the answer of the number of 5 subsets of this 10 set. You're given a 10 cardinal size set, you want to find all the number of 5 subsets. Okay, so this gives, I'm going to leave you with this definitions and then we will go. And an R combination is an unordered collection or unordered subset. A subset is sets are unordered, is an unordered subset of R objects from set n and a set of n objects. Okay, this value is equal to. Okay, so then we'll do the Johari tomorrow. Okay.